Hey babe, did you saw the picture in Twitter?
Oh, I forgot. Let me log into my account. Ugh, that's so sweet.
Warning. This is for educational purposes only.
In this video, we will learn how bad actors can combine different techniques to decrypt your HTTPS traffic. That includes forging network packets and exploiting an important default setting on a Windows computer. There are tons of resources in the internet about TLS decryption, but there is something they are not showing you. So the point of this video is to show you the crucial information you are missing, and most importantly for you to see the technicalities of the attack and how you can protect yourself from this. Before we go straight into building our attack tool, we must understand what is HTTPS and what is the role of a public key infrastructure. We spent most of our day visiting internet websites, so everyone should know what is the purpose of HTTPS. It encrypts your traffic, which protects you from bad actors sniffing on your personal data. There are several steps performed before the connection becomes encrypted. We will not dig into the details of each step, but I will just show just enough information to get you started. The source sends a client hello message, which signifies that the client wants to initiate a TLS connection. This contains the different cipher suites and maximum TLS version the client supports. The destination will now send a server hello message. It will contain the agreed protocol version and cipher suite, and it will also contain the public key of the server certificate. Asymmetric encryption using public and private keys are computationally expensive. For that reason, client and server will use symmetric encryption by generating and agreeing on a shared key. That will be transported using the server public key. The exact algorithm used to generate that shared key was determined on the first two steps. This transaction is also called client key exchange. Next messages after that will now be encrypted using the shared key. If connections to websites are already encrypted, then why do we still need certificate authorities? Imagine a scenario where people are happy using their favorite sites as they feel secure due to the benefits of TLS encryption. Then one day, a group of state-sponsored bad actors were able to compromise the servers without anyone knowing it. After that, they replaced the certificates with their own so they can decrypt the traffic. In the end, everyone is still happy as their connection is still encrypted. The question is, who will tell the users that the certificates are legitimate? That is the role of a certificate authority. These are governing bodies that verify the authenticity of websites. They are trusted by browsers on every platform. When getting a certificate for your website, you need to prove to the certificate authority that you are legitimate and the real owner. The certificate authority will verify your identity through several methods, such as checking your company information, phone call verification, and email validation. Once your identity is validated, you will be issued a digital certificate which you can use for your website. Any bad actor tries to trick users via malicious certificates will not succeed because browsers will prevent the users from accessing the site. So as you see, encryption alone is not enough to protect the users. You need to incorporate a trust system that will verify the authenticity of websites. Without that, the whole public key infrastructure will make no sense at all. Now that we have basic understanding about HTTPS, let's start with our attack chain by decrypting a traffic on the local network. Just to remind again, this video will show you the process to decrypt an HTTPS traffic on a local network. In order to do that, we need to change several techniques, which means it will not be as easy in real life as you see it from others. Most of them will just show a tiny part of it, but I want to cover a wider part of the process so you will know how to defend yourself in each segment of the network. So in this section, we will start with the core part of the attack chain, which is decrypting TLS traffic using MITM proxy. MITM proxy is a tool for intercepting all types of web requests, including TLS connections. It provides you several user-land binaries which you can use on different scenarios. First is the MITM dump, which is similar to TCP dump. Second is the main binary, which provides you an interactive console straight from the terminal. Third one is a web interface, which might be the most user-friendly. Let's check how we can run the main binary. It only accepts arbitrary options, but this is enclosed in square brackets, which means it is optional. So let's try to run it without any parameter. Okay, it's running, but we don't see anything yet since there is no traffic to intercept. You can also see here the different menu options at the bottom. Normally, proxies run on port 8080, so let's confirm. Let's add sudo to our command so we can also see the process names. We can see that it is really running on port 8080. Now let's try to generate a web traffic and pass it through the proxy. Let's add -L to follow the redirections. Then pass the proxy via -X flag. I have here my Kali IP, but you can also use localhost since the proxy is listening to all IP addresses. Let's execute our command. It was able to capture 2 requests. Let's pick one of them. You can also use your mouse to click on the items, which is really convenient. First part is our actual request. Then next is the response, which is a redirect to HTTPS. We can see here that Facebook is enforcing strict transport security, or HSTS. If you have been following the quizzes on this channel, you should have a basic understanding on what HSTS is. The last part provides more information such as server certificate. Now let's try to run the MITM dump. Then let's generate again a web traffic. The information on the output is much simpler from what we saw in the interactive console. I'm more familiar with this command, so I know that increasing the flow verbosity will produce more info, so let's do that. I'll generate again same request to Facebook. Now we see a lot of information. This is the command that we will use in most part of this video, so let's skip exploring this for now. Let's move on to the web interface. The dashboard produced by this command runs on port 8081. Let's open it. I'll generate again a traffic in the background. You see here that it resembles the Chrome developer tools. Aside from request and response, it also shows timing information, which is useful if you are debugging connection latency issues. Now that we have an idea on how MITM proxy is used, how can we use it to decrypt a TLS traffic? Well, the most basic way is to start first the proxy. I'll specify the listen IP address and port so to make it clear on where remote client can connect. We are looking for passwords, so I added an expression to filter relevant data only. After that, we can go to the target device and configure it to use that proxy. Let's go to proxy settings and set the proxy to our Kali IP address and port. Then open a browser and connect to any HTTPS site. At this point, you will see a warning saying that it doesn't recognize the MITM proxy certificate. In order to fix that, we need to download the certificate from the MITM website and install it on the client. I already have this prepared on the target machine, so let's install it. Remember from our previous section that strong encryption is not enough to protect the users from bad actors. We need to incorporate a trust system into the picture. In this case, the reason why we want to install the MITM proxy certificate is we want the client browser to trust it. Once trusted, it will appear legitimate to the browser. Now let's double-click the .p12 format. Let's install it for the current user for demonstration purposes. We will leave the password blank. Then we need to install this on the location where the trusted root certificates reside. Let's click Next and finish the installation. Now, if we try to refresh the page, the certificate warning is gone and we can access the site. We can also confirm here that the browser is now trusting the MITM certificate. Now, let's try to log into a site and capture the credentials. I'll use LinkedIn for demonstration purposes. I'll type some random password. Then let's go back to our attacker machine. Let's scroll up a bit. We now see the password in plain text. That means the TLS decryption is successful. Without going into the details, here is how it works in the backend. MITM proxy acts as the server to the client and client to the server. Once the client sends a request to the real server, MITM will intercept that message and get the hostname of the destination. Using that hostname, it will now generate a fake certificate signed by the trusted root CA we installed on the victim device. From that moment, the client believes that it is talking to the real server because of that fake certificate. That also means the MITM proxy can decrypt any further request from client since it has the private keys used to generate the fake certificate. As a result, it can intercept the shared key used for the symmetric encryption part of TLS handshake. Before forwarding the request to the real server, it will re-encrypt it using the real certificate. So that is how it performed the full decryption, acting as a man-in-the-middle proxy. Now, as I mentioned in the first part of this video, this is not easy in real life. The question is, how would you point the victim to our MITM proxy if you don't have access to his device? This is the point of this video. In order to arrive at a solution, it's best to list down some questions. Let's write some notes. Our first main question is, how are we going to point the victim to our proxy without accessing his device? Let's quickly go back to our test Windows machine. Let's look again at the proxy configuration. I will turn off the manual proxy since we don't need it anymore. If you notice, there is a section here about automatic proxy configuration. This is enabled by default on Windows machines. This is used for Web Proxy Auto Discovery Protocol, or WPAD. Before a client generates web traffic, it first tries to find if there is a host named WPAD or WPAD local domain. If it is successful, it will connect to that host and download a pack file. That pack file contains a list of proxies that the client will use for web traffic. If it wasn't able to find a valid WPAD host, then it will continue accessing the web pages without a proxy. This is the default Windows settings that we will exploit. That means our attacker machine needs to be the WPAD host. Being a WPAD host, we can serve a malicious pack file. That pack file will contain the IP and port of our MITM proxy. Next question is, how can we be the WPAD host? We need to spoof the DNS response to the client. That is by pretending to be the DNS server. But how can we do that? We can use ARP spoofing. This gives us a high-level plan for our attack. We need to perform ARP spoofing first so we can trick the victim that we are the DNS server. Then, as a DNS server, we can spoof a fake DNS response that will tell the victim we are the WPAD host. After that, the client will connect to us and we can serve him the fake pack file that will point him to our MITM proxy. Now that we already have answers to our questions, let's now start building our attack tool. Let's first plan the layout of our program. Let's create the main script called attack.py. Our attack will consist of several stages or techniques, so let's make separate Python modules for each. Let's put them under stage directory. Then, in order to let Python know that this directory will consist of modules, we need to create an init.py file inside. Now let's open our main file. Let's put the shebang on top. We know that we will use command line parameters, so let's import arg-parse module and initialize our parser object with some useful description. Let's just put some simple note like MITM SSL attack tool. Let's leave the arguments blank for now, but let's make sure anything we will add will be accessible to the global namespace. Since we will perform network attacks and packet forging techniques, let's add a condition that this should be run as root user only. Then don't forget to import the required modules, which is OS and sys. Let's create a main function as the entry point and put some placeholder for now. Then finally, let's allow the script to be run as standalone program or as a module. This will also call our main function. Now that our base layout is finished, let's start creating the individual attack modules. In this section, we will focus on the man in the middle module. In this module, we will use Scapy, which is a powerful packet manipulation library. I already published videos about this, so we will not dive into too much details. But for the sake of new viewers, I will give some quick overview. Let's first create our mitm.py file. No need to put a shebang on top, as we are just importing them from our main script. For all modules, we will define a function called run that will initiate the start of the actual attack. This is also the function that we will call from our main script. We will do man in the middle on the local network in order to pretend as the router or DNS server. That means we will be needing the router IP, so let's pass that as a function parameter. Then followed by the victim IP that we will attack. And we need also to specify the attacker interface we will use. We want to run this indefinitely, as this will serve as the foundation of our attack chain. That means the next techniques in the attack chain, such as DNS and WPAD spoofing, will depend on this, so we need this to be running always. There will be several exceptions that we might encounter, so let's put everything inside a try block. The Scapy method we will use is ARPMITM. The first two parameters it accepts are the two IPs we need to attack, which are the router and victim. This can be in any order. The last will be the interface we will use. Sometimes the victim may appear idle on the network or may experience disconnection, so let's capture an exception and retry the attack when we encounter that. Let's put 1 second pause in between so we will not generate too much noise in the network. If the attacker wants to cancel, we will handle that and exit properly. Let's add our imports. First is the time module, as we need it for adding the pause. Then sys for having proper exit codes. and our MITM function from Scapy module. Since we will have several attacks running on our program, it's good to have a nice indicator that a particular attack module has been started. We can use term color, which provides a better colorized print statements. This is not a default Python library, so you need to install this first. Let's add the unique message for this module. cprint works like normal Python print statement, but with additional parameters. First is the message, then followed by the color and the attributes. Let's make this stand out by making it blink and reversing the color to have a bold background. Before leaving this module, let's do a quick syntax check. We got one typo, so let's fix it. Now let's go on our main script and call our MITM module. As we just discussed, we need the router IP, target IP, and interface. So let's now populate our command line parameters and add them. Let's go to our main function. Scapy ARP spoofing function is a blocking call, meaning after it is started, it will prevent the next instructions in our program in executing. So let's run it in its separate thread using threading module. We will pass the module function, which is run, then the function arguments. After that, we need to start the thread. And finally, let's don't forget to import that module. And of course, the threading module also. Let's test this quickly. Make it executable. We will use ETH0 as the interface, then followed by the victim and router IP addresses. As you see, we have a nice indicator that this particular module has been started. Then it keeps on retrying because the victim is not reachable. So I will power on the victim virtual machine. Let's wait for a few seconds. The victim machine is up now and our program was able to detect it. Then it tried to perform the ARP spoofing. At this point, it is already sending fake ARP responses to trick the victim that we are the router. Our attacker MAC address is in the middle, and it is ending in EEFE. Let's remember this because we will verify this inside the victim ARP cache. Now let's go to the victim and confirm if ARP spoofing is successful. Let's open PowerShell and look at the ARP table entries. As you see, the router IP is now having our MAC address. That means we successfully poisoned the victim ARP cache. This confirms that our MITM attack module is working properly. Before building our next attack module, we need to satisfy some requirements before all these pieces work together. Since we will pretend to be the router on the local network, we need to act like a real router. The victim device still needs to connect to the internet to do normal browsing, so we don't want to disrupt that. So we need to forward those packets to the correct destination. Let's create a new module called router. We need to execute a Linux command to allow packet forwarding, but we may need to execute additional commands along the way. So let's prepare a list as a place to put them. Now let's add the command needed to forward packets. This is the same as sending a numeric value of 1 to /proc. Same with other modules, we will define a function called run. In this module, we don't need to pass any function parameter, so let's leave this blank. Let's put some message that we will execute some OS commands. Then we will loop through our command list. Let's also display each command we will execute to give us idea on what's happening. These messages doesn't need to be too recognizable, so let's just use a light color. Then we will use subprocess module to execute each of them. Subprocess accepts a list as input, so we need to split each command via a white space. We don't care about the output and error messages, so let's pipe them to dev null. If the command fails, we will return an error and exit the script, as these are prerequisites that needs to be met before the other modules will run successfully. Let's do our imports. First is the subprocess for executing the actual commands, followed by sys for the exit codes. Then term color again for a better way of displaying the output. Let's now go to our main script and import this module. We will just add it to the existing imports. We don't need to run it on its separate thread, so let's just call the run function. Let's test quickly. We see the message. I'll hit Ctrl+C and verify if it is successful. The IP forward kernel parameter is now set to 1, so that means the command execution is successful. This also confirms that our router module is working properly. Now that our man-in-the-middle ARP spoofing is working as expected, let's go ahead and build our DNS spoofing module. Do note that this is the most complicated part to build, so please pay attention. I find this trickier to do compared to ARP spoofing, and I encountered several issues. Don't worry, we will tackle those important points in a second. Having said that, let's first have a high-level overview on how this attack should work. In summary, we already have a strategy for the two items on our attack chain, which are the ARP spoofing and the actual MITM proxy attack. In this module, we will go further ahead on the attack chain, which is to spoof the DNS response for WPAD host. With the help of ARP spoofing, we were able to trick the client that we are the router. In most cases, routers on local network serves as the DNS server as well. So that means any DNS queries from the victim will go to us. The DNS query we are expecting from the client is the one for WPAD host. Once that DNS packet arrived on our network interface, we will prepare a fake DNS response. That response will tell the victim that the attacker is the WPAD host. A DNS packet consists of several information, but we will not discuss all of them in detail. But we will go through the important bits within our program. So let's go ahead and start coding. Let's create our DNS module. Then same with others, let's define the run function. Since we will do packet forging in this module, we will need the router IP, target IP, and interface, so let's pass it to the function. This is one of the main techniques in our attack chain, so let's put a bold message similar with MITM ARP spoofing. But this time, let's use a different color. We need to get the DNS packet that will arrive on our interface, so let's use scapy-sniff function to do that. We need a dedicated function that will do the packet forging, and we need to pass it to PRN parameter. Let's name it as poison response. Do note that I put underscores to signify that this is a private function and not intended to be called from our main script. We want only the DNS packet, so let's use a BPF filter. Lastly, the packets will arrive on the interface we are using for our attack, so let's specify it as well. If you notice, there is no option to pass information to the scapy processing function. We need to find a way to do that. One option is we can use global variables so the processing function can get their values. So let's try that. First one is for the attacker IP. Next is the router IP, followed by target IP, and another one for the WPAD hostname. We just initialize them as global variables, which means they can be accessed anywhere within the module, but we still don't have the actual values for them. So let's put the values. We can easily get the attacker IP by telling Scapy to return the IP associated with the interface we used for our attack. We already have the router IP passed to this module, so let's use that value. Same thing with target IP. We will set the WPAD hostname to wpad.local domain. This is something constant, and we don't intend to change this, so it is okay to hard-code its value. Next thing we need to do is to construct the proper BPF filter that will get only DNS query packets originating from the victim. Let's use Python fstrings so we can reuse some variables. We will filter packets destined to port 53, but not originating from our attacker machine to exclude unnecessary DNS packets. But make sure it originates from the victim machine. Now, let's go a few lines above to create our packet processing function. Scapy implicitly passes the packet object, so let's add a placeholder variable for that called PKT. This may be the reason why we cannot pass custom parameters, forcing us to use global variables. Since this is DNS spoofing, we will get the query name of the original packet so we can reuse later. We can easily extract it from the DNS question record layer. If it contains our WPAD hostname, then that means it is the DNS query that we are looking for. That value is a bytes object, so we also first need to convert it into a string. Constructing packet in Scapy is very easy. It is done by stacking the different layers. Then we can manipulate each layer by setting the necessary attributes. Let's prepare our layers, starting with IP layer, followed by UDP, since we are dealing with DNS, then the upper DNS layer. Last will be the DNS resource record layer, which will contain the actual spoofed data. Let's start modifying the attributes of each. First is the IP layer. The source IP address will be the router so that this will appear legitimate to the victim. Destination IP will be the victim. We don't need to do anything else on the IP layer. Those settings are enough, so let's move on to UDP. Since we are acting as the fake DNS server, the source port will be port 53. Then the destination port is whatever source port the victim used for this connection. This may be confusing, but it is important to have the correct details to make sure we are using the proper UDP connection. On the DNS layer, we first need the ID. This is a unique identification number set by the victim. We need to make sure this is also correct, so this spoofed response we will return to the victim won't get lost. So let's just reuse the ID found from the original packet. Next will be the query data. When sending a DNS response, the original query data is always included, so let's also reuse the one from the original packet. Next is the authoritative indicator. Setting this to 1 will tell the victim that we are authoritative for the record, so let's set it to that value. QR indicates whether this is a query or response. Let's use 1 since we are responding back to the victim. The next attribute is similar to QR. We will also set this to 1 as we are providing an answer. The last layer will be the DNS resource record, which will contain the actual spoofed response. QName will be the WPAD host followed by a dot at the end. The next attribute will be similar with QName. I didn't really research that much about this 2 attributes, so not sure yet what is the difference. The last one will be the actual IP address of the record the victim is looking for. We will set this to our attacker IP. We finished crafting our packet, so let's send it. We will use the send function from Scapy and set verbosity level to 0 to prevent putting too much noise on our program output. Let's also put some useful identifier that will tell us when spoofing is successful. Now, let's add our imports above. There are a lot of functions and classes we use from Scapy, so let's make sure we import all of them. Then we use also cprint from term color, so let's import it as well. Now let's import this module from our main script. Same thing, I will just add this from the existing imports. Then we need to run this in its separate thread, so let's just copy the format from MITM module. Now let's try this out. I will rerun same command. We can see here that our fake DNS server is running. Same thing with ARP spoofing. Let's go to the Windows machine and verify. We will open PowerShell and do a query for wpad.localdomain. .132 should be the attacker IP, but let's confirm it inside our Kali. Let's list the network interfaces and grep for that IP. We are right, that's the correct address. This means our DNS attack module is working good so far. Before we start building our next attack, let's do some necessary improvements in our DNS module. On our previous section, we successfully tricked the victim to believe that we are the DNS server. That means aside from WPAD host queries, the victim will also send us queries for other hosts such as internet sites. But the logic of our code is to handle only queries for WPAD host. That means other queries will just be dropped and the client won't have full network connectivity. In order to fix that, we need to forward any other packets to Google DNS, get the response, and send it back to the victim. Since we will use Google DNS, let's create a global constant for it. Let's use the quad 8 DNS address. Then add an else condition that will handle other types of DNS queries. First task is we need to replicate the DNS query we got from the victim and forward it to Google. As we saw from the logic above, constructing DNS packet requires several information. This time, let's try to simplify and only put the things we think is needed. If something fails, we can just add more attributes until issue is fixed. Let's create the forward packet layer. Destination IP address will be Google DNS IP. For the source UDP port, let's try to use the original source port from victim. But honestly, not sure if this matters since Google is not the one that will respond to the victim. Let's set RD to 1 so that the record will be searched recursively. Then the query data will just be the one from the original packet sent by the victim. We can easily construct this via the DNS QR layer from Scapy. We need to send this to Google and get the response back. So let's use Scapy send and response function. We will pass the packet and set verbosity level to 0. it's better to store the response in a variable so we can reuse it later. After we get the response from Google, we need to send it back to the victim. So let's now craft that response packet. And we again need to prepare the layers. On the fake WPAD response packet, we set the source IP as the router IP. Just for fun, let's see what will happen if we set this to our attacker IP. Destination will be the victim. As mentioned a while ago, destination UDP port will be the source port used by the client, so we can connect back properly. Then finally, we can just set the DNS layer to be the same from Google's response packet. This time, we are not expecting any further response from victims, so let's just send this packet straight away. Let's don't forget to import the SR1 function. Before we test this, let's quickly go back to our router module. When I'm testing this attack, I encounter issues when the client tries to perform other DNS queries. I didn't get proper responses, and it turned out I needed to accept the packets when passing through the IP table's forward chain. So let's add the command that will do that. Then let's also flush the firewall rules before executing any further command to make sure everything is clean. Now it's time to test this. Let's first rerun same command. Then let's go to the victim machine to perform some DNS queries. Everything should succeed, regardless whether it's for WPAD or other hosts. Let's try first the WPAD. It is still working as expected. Now let's try google.com. Something wrong on the output. It appended local domain on the hostname, but the IP address looks a legit routable IP. There might be some bug on our code. Let's try to ping something outside as an added verification. Still looks okay. As a final test, let's see if we can still browse the web. Accessing Facebook works properly. Let's try another one. Same thing with Wikipedia. Everything is being loaded properly. Everything works as expected, so let's go and build the last module. This last module is the most simple to build. We will create a web server that will serve our fake pack file. Please stay with me as we are almost finished. Let's create our HTTP module. We will only be needing the interface as a function parameter. This is where we will run our web server. Let's define two constants, the HTTP port and the attacker IP. We can reuse same technique on previous sections to get this. That is by extracting it from the SCAPI configuration settings. Since this is an attack module, let's put some nice identifier. But let's use different color. Let's initialize an instance of HTTP server. We need to pass the port and address as a tuple. Then the next parameter will be the handler type. We will only handle basic GET requests, so let's use the simple handler. Finally, let's run the web server indefinitely. Before we go, let's import the required modules. Then back to our main script, we will import the HTTP module and run it also on its separate thread. As a final task, we need to create our pack file. This is a JavaScript with a standard format. We need to name our function find proxy for URL since this is the format browsers are looking for. And finally, let's return the proxy import which points to our MITM proxy. It's time to do this. First, let's open up MITM proxy and leave it running. Then run our attack tool. I'll power on the test Windows machine, so let's wait for a bit. We got a hit. Now, I'm going to simulate someone who is signing in to a website. I'll enter some username and some random password. Let's go back to our attacker machine. Scroll up a bit on the MITM proxy output. We can see here the plain text password. This means we were able to decrypt the TLS traffic. Before we end this video, I want to take note of some important points. Spoofing is very easy to do on local network. This is one of the most used techniques by bad actors as a foundation for other higher level attacks. Some of the default settings on our computer can be exploited, so let's be aware of that. Better to disable them if not needed. Thank you for joining me in this video. I hope you learned a lot, and please don't use this technique for malicious purposes. Lastly, if you notice we didn't tackle the stage 4 of our attack chain, that is how attackers can install malicious certificates on our trust stores. This is a wide topic as there are a lot of ways on how to do it. We will discuss this on the next videos.
So please stay tuned.